so I'm going to talk a little bit now on the open source software project, the Storage Performance Development Kit, and how you can use it to accelerate NVM Express. So I think I think everybody here, pretty much knows the NVMe specification and what it's done to enable highly optimized storage drivers. The specification, there's no register reads in the I/O path, which is much more efficient compared to specifications like HCI. All operations are done on host memory, or even on some architectures, a lot of the operations are actually done on LLC. Plus multiple I/O queues, tens, hundreds, or even thousands of I/O queues allows each CPU core or execution thread to have its own queue for submitting I/O. So these could all happen in parallel without requiring any locks. But even with all of that, the best-of-class kernel mode drivers today have a non-trivial amount of software overhead. We've measured this anywhere from 3 to 5 microseconds on a per I/O basis for the Linux kernel drivers. So for general purpose applications, this is generally okay, and the kernels have to support hundreds of usage models. They have to cover every usage model for every application. But for some applications, some storage appliances, there are some optimizations that you can make. So when you start looking at NVMe SSDs that do 500,000 or more I/Os per second per drive, you can get 2U servers today pretty easily that can support up to 24 SSDs in a single system. You can see how these boxes can do millions of I/Os per second, and those 3 to 5 microseconds per I/O can really add up. But it's not just an efficiency issue either. Now that we start to look at media that can get sub 10 microsecond media latency, that 3 to 5 microseconds that's on top of that is just eating into the performance. And so that's really where the Storage Performance Development Kit, SPDK, really comes into play. I'm going to talk a little bit here about the pulled mode user space drivers that the project has for NVMe. So first, a little bit of an overview of what SPDK is. It's an open source software project. Intel started it about 4 years ago. About 2 years ago, it was open sourced on GitHub. It's BSD licensed. For those that know BSD, that you know why this is important, but for those that don't, this means that your company can take this source code, you can use it as is, you can modify it, you can reference it. It's a very permissive license, and the changes that you make to it, you can keep proprietary if you wish. Of course, the SPDK project, we really welcome contributions, and we've had a number of companies submit improvements to the project. You can get access to the source through GitHub. We have a project website at spdk.io. SPDK is really a set of software building blocks. I'm going to go into a little bit more detail on that here in a second. There's pulled mode and user space drivers and protocol libraries, not just for NVM Express, but for another number of other protocols and storage use cases as well. And it's really designed for not just current, but also next generation NVM media latencies. So I know there's a lot of blocks here, and we're not going to have nearly enough time to go through all these today. But just kind of wanted to touch on the different pieces that are here and some of the different layers. This bottom box here, the drivers, that's what I'm going to focus mostly on today from an NVM Express standpoint. We also do have a Intel Quick Data Technology driver. Some people might be more familiar with the name Crystal Beach DMA. So there's a user space DMA driver for that as well. This middle box is a storage services. So pretty much any kernel today, you have to have a block layer, right? And if you start to move drivers up into user space, you need to have block layers to build applications on top of it. And so we provide some block device abstractions that then we can start building storage services on top of. And I'll talk a little bit at the end of the presentation about a couple of examples of this and some other talks that will be here this week. And then on top of some of the storage protocols. So now that you have this storage, how can you present it over a network, or also from a virtualization perspective with vhost virtual machines? Okay, so first, the NVMe PCIe driver. The driver supports 1.0 to 1.3 spec compliant devices. So pretty much any NVMe device that you have will work with the SPDK driver. We do have a Quarks infrastructure because there always are idiosyncrasies with all the different SSDs. The biggest aspect here is that these drivers do run in user space. So, for example, SPDK runs on both Linux and FreeBSD. In both these operating systems, the kernel driver no longer controls the device. We use user space I/O frameworks to take control of the device from user space. And we use an asynchronous pulled mode operation. And this is really what starts to cut into a lot of the software overhead that I talked about earlier. I'll show some data on that here in a minute. And the storage application or appliance owns all the IOQ allocation and synchronization. So traditionally in kernel mode drivers today, the kernel basically usually tries to allocate one IOQ per core. Sometimes you don't always get a one-to-one mapping. You may have more cores on your system than you have IOQ, so there's some sharing and stuff that's involved. With SPDK, we basically sort of put on the application to own the IOQ allocation. The application is going to be designed to know best how the IOQ should be allocated. And if it does need to do any kind of synchronization, we put that up in the application layer. What we really want is for this to be completely lockless and to get rid of a lot of the overhead. And so what we found is for applications that can be redesigned to take advantage of it, they can get rid of a lot of this software overhead. There are a number of optional features that SPDK does support, end-to-end data protection, SGL for devices that support that in addition to PRP, reservations, namespace management, weighted round robin, controller memory buffer, firmware update. The last one is hot plug. Obviously, with NVM Express, these are PCI devices. Supporting hot plug in a user space driver is actually fairly challenging. This is something that we've added over the last year, and now you can do safe hot plug surprise removal with SPDK. So next, one of the items that we've added to SPDK within the last year is an NVM Over Fabrics initiator. So when the spec was released, the NVM Over Fabrics spec was released last year, SPDK had a target ready when the spec was released. But one of the things we've added now is an initiator as well. And what we really wanted to do was to provide a common API. So for people who have already developed applications with SPDK to talk to local PCIe devices, now you can use that exact same API to be able to talk to remote devices as well. This gets a little bit into what Parag was talking about with the Linux driver. The Linux driver does something very similar. It has a lot of core logic for NVM Express, and it can differentiate versus either local PCI or remote devices as well. And the pro parameters differentiate which device you're going to be accessing. It's a pluggable fabric transport. RDMA is the one we currently support. We build on top of libIBverb, so it's standard. Really, as long as libIBverb supports the RDMA NIC, SPDK will support it as well. It is pluggable. You've probably seen on some of the roadmaps for the NVMe working group that a TCP transport is being worked on, and so you can expect to see that in place too once that's worked through the working group. So next, just to talk a little bit about some of this performance overhead that I've been talking about. So this first chart shows the software overhead in terms of nanoseconds for both the submission side and the completion side. And then we're comparing the Linux kernel versus SPDK. So you can see the aggregate here is somewhere on the order of 5 to 5.5 microseconds, and this can vary a little bit depending on what your system is, but it's pretty consistent. It's in that 3 to 5 microsecond range. And with SPDK, we can cut this down to on the order of about 500 nanoseconds total. So now we've saved ourselves, anywhere from 2.5 to 4.5 microseconds on a per I/O basis. So a lot of these things come from just a lot of the things that a general purpose kernel driver has to do. Like SPDK is not a drop-in replacement for a kernel driver. That's not what the intent here is. The kernel does what it does because it has to do all the things that it does. So with this type of user space framework, we're pre-allocating huge pages. So typically an appliance or a storage application, it knows up front how much memory it needs. We can register that memory up front. We don't have to do address translation. We don't have to pin that memory. That saves us time. On the completion side as well, we're polling, so we can avoid all that interrupt overhead as well. we're actually polling on those completion queues. So the second that the NVMe device has flipped the completion bit, we know that the I/O is completed and we can send it back to the application. So this really, kind of shows now where when you start looking at media that has, sub 10 microsecond latency, now you can start to see better performance, not just better CPU efficiency for some of these queued up 1 workloads. And then from an efficiency perspective here, we're just kind of showing, just using a single Intel Xeon core, is we start ramping up, just running just 4 KIOs on a single core. How many drives can we saturate? The Linux kernel actually, does a good job. It gets about 500 KIOs per second per core, which for most systems is plenty. But when you start taking systems that have many more SSDs in them, you can see where it starts to really chew into the number of cores you have available for doing other types of storage processing, dedupe, encryption, compression, etc. So with SPDK, we can max out 8 of the Intel P3700 SSDs. Okay, so finally, I'm just going to touch on a couple of I guess, upper level usage models for SPDK. So the first one is called Blobstore. So this is all great. We've got these block drivers, but most applications don't consume blocks. They want file systems, or they want to partition a device into multiple logical volumes. So what do we do about that? That's where the SPDK Blobstore comes into play. This is a building block that the SPDK community open sourced earlier this year. It's a user space general purpose block allocator. There's a number of usage models and components that we can build on top of this. The first one is logical volumes. So again, now that SPDK is building things up in user space, you don't have things like Linux LVM to be able to partition your SSD. So SPDK logical volumes is something we're going to be releasing later this year. This enables you to do that kind of dynamic partitioning. So in the absence, if you have SSDs that don't have namespace management, or you don't have SRIOV, this allows you to do some of the dynamic partitioning to be able to divide SSDs up into logical partitions. And finally, something called BlobFS. There's actually a lot of use cases today where an application needs a file system, but it needs a pretty bare bones subset of what a file system can do. If you look at things like RocksDB, it has a storage plugin. The RocksDB key value engine, it usually creates anywhere from 100 to 200 files. They're pretty large, typically just doing write only, append only, random reads. And so there's some basic file system support that we've added to SPDK to support those kinds of use cases. And we've included a RocksDB integration in there as well. If you could travel time, you could go back to this morning and you could go to Forum D11 and you could hear a talk on SPDK Blobstore. But without having that, you should be able to get to the slides online after the summit's over. And finally, vhost. So traditionally, SPDK has been focused on storage networking type of workloads. So iSCSI, NVMe Over Fabrics. But on the networking side, a long time ago, they basically took VirtIO and they took vhost as a way to accelerate virtual networking into virtual machines. And the DPDK project took this and created a user space vhost target, which even more drastically accelerated being able to handle network packets for these VMs. So the SPDK project has taken these technologies and extended them into a storage context. This allows us to do a couple of things. One is reduce the I/O overhead on those I/O processing cores. So all of those charts that I showed you earlier, where we're cutting down the amount of overhead you have on a per I/O basis, well, now we're able to do that for these SSDs that we're serving into these VMs. But not just that, but the VMs themselves. So if you're familiar with how the VirtIO drivers work, Whenever they submit an I/O, they need to ring a virtual doorbell, which causes a VM exit. Well, with SPDK, since SPDK is polling for these I/Os, we can avoid those VM exits, and we can also get better CPU utilization inside of those VMs. So now those VMs can free up CPU cycles to not just do I/O processing, but to do the application that they've been launched to do. If you're interested, there's going to be a talk I'm going to be giving on Thursday afternoon in Forum W32. It's going to go into this in some more detail.